So I've got good news, guys. We're almost done with this class. Believe it or not, there's only 3 lectures left, including today's. So that means 2 after today, if you couldn't do the math there. And I've got other good news. So for obvious reasons, I don't tell you guys this at the beginning of the course. But honestly, this is probably the least interesting course. I mean, don't get me wrong. If you've been excited and enjoyed it so far, that's all the better. But basically, every course that comes after this is way more exciting. Because right now, we're just solving for voltages and currents. And I get you kind of got an idea what those are, but it's got to be hard to see how a bunch of voltages can, make a computer, right? It's kind of hard to play Fortnite on a bunch of voltages. Starting the next class, digital, we get to see how all of this makes those things happen. And so I'm really excited for where you guys have made it so far and what we're going to see next semester. We've got just a few of these left, and then we're done with this and on to the fun stuff. Not that this isn't fun. This can be fun, but it can be more fun too, right? It could always be more fun. All right, let's start this. Thevenin equivalent circuits. Basically, the idea here is that we can take any resistive circuit. So any circuit that's made up of resistors, no matter how complicated it is. It could have like 50 voltage sources, 200 resistors. No matter how complicated it is, we can shrink it down to something that looks like this from the load's perspective. And that means instead of solving a huge circuit, I can just break it down to this and solve a much smaller one. Let me give you a more practical example. Why? Let's say I have this circuit, right? I'm building, I don't know, the next Amazon Echo, or the next, whatever you want to call it. Some sort of weird amplifier that's got a bunch of stuff going on here. But let's say this is designed so that the user can stick a speaker right there. The problem is, there are a bunch of different types of speakers, right? And so we don't know, will the user use a 50 ohm? Or will the user use a 100 ohm? Or a 500 ohm? What we need to do is we need to calculate the current through this speaker for any of those values. I'm going to try it with all 10 values. Now, I don't know about you, but I don't much feel like breaking this circuit down 20 different times, right? That would be horrible. We wouldn't want to do that. I teach this stuff. I definitely don't want to do that. And so instead what we can do is we can reduce this whole circuit to just one voltage supply and one resistor. Even though it's got so many resistors and so many voltage supplies, we can reduce it to this and then try all of these values just on that. So that's why we have Thevenin circuits. So this is kind of a simple contrived example, but there's a lot of cases that are like this. In fact, I'm going to show you one problem that you think you can solve now, but you actually can't because it's tricky. All right, let's get to it. How? Here's what we do. It's only 2 steps, right? It's kind of like professors always say, it's 2 steps and there's like 5 parts to each step. No, it's not that bad. What we need to do is we're going to have to pick what is the load. So in the example I just showed you, that was the speaker. Basically, remember the load is the useful part of the circuit. So we're going to pick what is the load and we're going to open the load at that point. This is actually going to make it easier. We're going to open the load at that point and calculate what would the voltage be across that load. After we have that, we're then going to remove all the sources and calculate what would be the resistance from the load's perspective. Honestly, everything we're doing is pretty much the same as we've been doing, except this step, since we're going to be calculating essentially total resistance, but not from the source's perspective like we normally do it, but from the load's perspective. And now I'm sure you are totally 100% confused, so let's just go to examples so I can show you it's not actually that confusing. Alright, so let's say I have this circuit. And what I want to do is I want to know what is the current through the load when RL equals 1K and when it equals 5K. So I want 2 different values here. Notice that I've already indicated on here what our load resistor is. So we want to try it with 2 different values. I don't want to have to break this thing down twice. And imagine if I wanted to know it for 10 different values. And so what we need to do is we need to follow those 2 steps. Remember, step 1 is to open it at the load. And so what I'm going to do here is I'm going to redraw the circuit for step 1. So we have 10 volts. We have 1K. We have 3K. And now remember, I'm going to open it at the load. So instead of drawing that RL, we open it. And now all we have to do is figure out what is the voltage across that point, where the load used to be. We call this the Thevenin. Alright, so let's solve it. Just like before, we just have to shrink our circuit. So this, right, notice again, just like some of our previous examples, because there's only one way for the current to flow, current can't go this way because it's open. So see, I told you, this kind of makes it easier for a lot of problems. Current can only go that way, and so we have two resistors in series. So this would become 10 volts, 1K, and 3K in series gives me 4K. Just like before, we can now calculate the current. So let me open up my trusty calculator. We have 10 divided by 4E3. So that gives me a current of 2.5 milliamps. So the current going this way. Wow, why are all my markers so huge? What did I do? Let me make them smaller here. So we've got the current going this way of 2.5 milliamps. And so I can take, now I know the current going this way is 2.5 milliamps. And so just like before, we need to solve for our voltages. So if I have 2.5 milliamps going this way, and I have a 1K resistor, that gives me 2.5 e to the negative 3. I wish I had a negative button on my keyboard. Times, what was it? 1K. 1E3 tells me that I have a 2.5 volt drop across there. So from here to here, we have a 2.5 volt drop. Now, let's think about this, right? This is our ground. So what is the voltage at this point? Well, the voltage at this point is 0 volts because it's connected directly to ground. We can see that here. What is the voltage here? Well, it's 10 volts here, and from here to here, we drop by 2.5 volts. So that means the voltage here must be 7.5 volts. And notice, this is just a wire. So if it's 7.5 volts here, and it's 0 volts here, then the difference across our Thevenin is 7.5 volts minus 0 volts, or 7.5 volts. So that's it. We've done step one. We've solved for the difference across that open. Now we need to do the second part. So remember, step two is we need to open it at the load, get rid of our sources, and calculate the resistance. So just like when we did superposition, to get rid of a voltage source, I just short circuit it. We have 1K here. We have 3K here. We leave this open. And now what I need to know is what is the total resistance? That's our Thevenin from here to here. Now I always encourage you guys to redraw and trace it. I'm definitely going to do that for this. We're looking at it backwards and sometimes that makes it confusing. So I'm going to redraw this as I trace it. So I'm going to start here. So if I start there and I follow this along, I keep going until I immediately notice I have a choice. So before I even keep going, I'm going to write that choice. I have a choice. If I follow it across the top path, I have to go through a 1K, and then I'm where I want to be. So I'm going to write that. I have to go through a 1K, and then I'm where I want to be. If instead I take the bottom path, I have to go through a 3K, and then I'm where I want to be. So I'm going to indicate that. I have to go through a 3K, and then I'm where I want to be. And so all I need to do now is solve this to get our Thevenin. And so since we have a 1K and 3K in parallel, I can do 1 E3 1 over X plus 3 E3 1 over X equals 1 over x. So we get our Thevenin value is 750 ohms. That's it. We've solved for the Thevenin. So now what I'm telling you is that this circuit up here is exactly the same as this circuit, where we have 7.5 volts and 750 ohms. So anything that I attach to this circuit right here will be exactly the same as if I attached it here. And so our problem said it wanted to know the current if our load was 1K. Well, if our load is 1K, then that means our current would be 7.5 volts divided by these two right in series, so 1.75K. And if we do that, we get 7.5 volts divided by 1.75 e to the 3. And we get looks like 4.29 milliamps. If instead of 1K, the user bought some sort of external peripheral that was 5K, we would have I is equal to 7.5 divided by 5.75K. And in that case, 7.5 divided by 5.75 E3, we would have 1.30 milliamps. And so notice, by shrinking this down into its Thevenin equivalent, which is this circuit right here, this is the important part. You gotta know the Thevenin equivalent. I can test as many examples as I want really quickly without having to break this huge circuit over and over again. Okay, I get it. This is not exactly a huge circuit, but imagine if it was a huge circuit. This is way easier. You ready for another one? I gotta show you more than one example. Come on. Let's look at another one. Okay, so let's try this one. I know what you're thinking. This is like almost the same problem. It's not. It's kind of different. It's a little bit different, right? There's an extra resistor here. And you solve it the same way. It's pretty much the same. But I want to make sure that there's a trick to this problem I want to make sure you notice. So again, remember, step 1, open it at the load. That's this guy right here. And solve for Thevenin. So we'll redraw it. 20 volts. We got a 2K. We've got over here a 500. 6K. And then again, we open it at the load. Always open for Thevenin. So we've got Thevenin right here. And so we need to figure out what is the difference between those 2 points, and that is our Thevenin. So again, we just need to break this down, and I wanted to point this one out specifically because again, notice, how does the current have to flow? Well, the current flows this way, it comes up to here, and all of it must go down. Again, remember, if it's an open circuit, we can't have any current going that way. So actually, when we're solving for Thevenin, this breaks down the exact same way. And so we have, in this case, a 2K in series with a 6K. So when I shrink that, we've got 20 volts. And so notice it's like that 500 is not even there. It will be when we get to the resistance though. That's why I wanted to make sure I did this problem for you. Alright, we've broken it down as far as we can. So now we need to solve for the current. So I pull up my calculator. And we have 20 volts divided by 8E3. And we get 2.5 milliamps. Isn't that what we got before? How are we getting the same number? 2.5 milliamps. And so again, that means my current going this way is 2.5 milliamps. So we can solve for the voltage drops. So I've got 2.5 e to the negative 3 times 2K. That gives me a 5 volt drop across the top. So from here to here, we have a 5 volt drop. I'm going to do this just to show you it's the same. We don't actually need to solve this one. But if we have 2.5 e to the negative 3 times 6k, so 6e3, we get that we got 15 volts here. So 15 volts. And again, remember, this is our ground. And so again, we just need to get the difference between here and here. If this is connected to ground, so it's 0 volts on this side. Notice if it's 20 volts, and we go down by 5 from here to here, this bump must be at 15 volts. And again, that makes sense, because notice if I started here and we're at 0, and I go up by 15, then that shows me, yes, I did this correctly, I'm at 15. The part I wanted to make sure is, what is the voltage here? Well, remember, the drop across this resistor is equal to V is equal to I times R. But remember, there can be no current going this way. Current is 0. So that would be 0 times 500, which means the voltage drop across this resistor. So the voltage from here to here has to be a 0 volt drop. So if it's 15 on the left side, it drops by 0. This has to be 15 volts as well. And so the difference, V Thevenin, is the difference between those two wires. It's 15 volts on one side, 0 volts on the other, and so our V Thevenin value is simply 15 volts. So no, it's not new. Same thing we did before. Just want to make sure everybody remembers it. I trust you, but not totally. Alright, now we got to do the resistance thing. So remember, to calculate the resistance, we have to get rid of all the sources. So because it's a voltage source, we short it. Remember, if it was current, we'd open it. We'll do one of those examples. We then have 2K. We have 6K. I have 500. And then I need to solve for the resistance looking from the load's perspective. So from the output's perspective, from here to here. And now notice that 500 ohm does matter. So it didn't matter at all when we calculated the voltage, but it matters when we do the current. So like I said before, what you want to do is redraw it, because it can be confusing. So if I start here, I have to go through a 500, and then I hit a choice. So I'm going to draw that over here. I have to go through a 500, and then I hit a choice. Okay? At this point, if I go one way, I have to go through a 2K, and then I'm where I want to be. So I draw that. I have to go through a 2K, and then I'm where I want to be. If instead, though, I go the other way, I have to go through a 6K, and then I'm where I want to be. So I have to go through a 6K, and then I'm where I want to be. And so this is it. We just have to now solve this for its resistance. So again, if I were to shrink this, we would have a 500, and then we have 2K in parallel with 6K. So I have 2e to the 3, 1 over x, plus 6e to the 3, 1 over x, equals 1 over x. So we get 1500. And so if I add these up, I get one resistor of 2000, which again, remember, is the same as 2K. And so that's it. We're done. So again, this circuit, basically from the left side over, is exactly the same as if I had just built this. What was the value? I forgot it already. 15 volts. 15 volts with a 2K resistor. And so now anything I want to attach to this circuit will be exactly the same as if I attached it here. And so it makes it a much simpler circuit to solve. Any questions? Oh, that's right. Well, since you can't have questions here, send me a message on Discord. You guys are starting to ignore me. I heard from you all the time in the beginning. Now I'm not hearing so much. Alright, what about this circuit? First of all, what is this circuit? I want to hear 100 people tell me what the circuit is, even though there's only like 24 people in the class. This is the Wheatstone Bridge, right? We just covered it last week. Here's the thing about the Wheatstone Bridge. Do you know you can't solve this circuit? I know you can balance it, because I showed you how to balance it, but believe it or not, you don't know how to solve this. Right? Normally in class at this point, I make students stop and try to break it down, kind of like as a sick joke, because you can't, right? Let's try to break it down. Well, the 2K is not in parallel with the 4K, because there's a 1K between. They don't share the same bottom. And the 2K is not in series with the 3K, because the 1K is in the middle. So at this point in the class, even though we've covered almost everything, you don't have any way to break this circuit down. And the reason is it's not clearly in series or in parallel. It's something called a delta that makes things way more complicated. But notice, that 1K resistor, remember this was our load. This was the LED in the last lecture. If I break this down to a Thevenin, I can solve for this. And so that's exactly what we have to do. So I'm going to redraw it. I have a 2K here. Again, we open it at the load. I have a 3K here. $4K and $5K. And so now, from here to here, this is our Thevenin, the difference between those two sides. So like I said, this was a really confusing problem because we couldn't even break it down. Thanks to Thevenin, we can. And so, we have, from this point on, just breaking it down like we always do. I've got two resistors in series on both sides. So this would become 15 volts. 2K plus 3K gives me 5K. On the other side, we have 4K plus 5K, which gives me 9K. I could break it down another step, but I don't actually have to. All we need to get the voltage are the currents on this. So let's do that. Before I had you solve every possible thing, now let's just solve for exactly what we need. I need the current here, and I need it here. So I've got 15 volts divided by, why do I keep forgetting? 5K. So we have 3 milliamps on the left side. You should know it now, but just in case you don't, remember all I'm doing is I is equal to V divided by R. The voltage across this is 15 volts, and so if I divide 15 volts by 5K, I get the current. On the other side, we have 15 divided by 9 e to the 3, and we get 1.67 milliamps. Again, bring this information back. So that means from here to here, I have 3 milliamps. From here to here, I have 1.67 milliamps. Now remember what we're trying to solve for. We know this is ground. What I need is I need to know the voltage at this point and at this point. So the easiest way to get that is to just solve for the voltage drop across the 3K, because that'll give me it directly. And solve for the voltage drop across the 5K. So I've got 3 milliamps times 3K, and that gives me 9 volts. So I have 9 volts here. And on the other side, we have 1.67 e to the negative 3 times 5K, 5 e to the 3. And that gives me 8.35. So I've got 8.35. And so now we're able to solve for our Thevenin, the difference between this spot and this spot. Because on the left side, that spot is 9 volts. On the right side, it's 8.35 volts. And so our V Thevenin value is, looks like 0.65 volts. That's it. V Thevenin. Now, let's get the R Thevenin. And this one is way more confusing with this circuit. So make sure you pay attention to this. So again, remember, we short out the 15 volt source. We had 2K here. We had 3K here. 4K, and 5K. This is probably the most confusing resistance one to calculate, so make sure you pay real close attention. I need to know the difference from this spot to this spot. Always redraw this one. Okay, so watch what happens here. I start here, and I go. And I have two ways that I can go, so I'm going to indicate that. If I go this way, I go through a 2K. But notice, after I go through that 2K, I'm at this spot. I'm at the same spot as if I went the other way. So I need to indicate that. So this was the 2K. If I go through the 3K, I go through it and I'm at the same spot. It's rejoined the other side. So this is our 3K. So notice how it joins back up with the other side. It's important to notice this. At this point, I have two choices. I can go this way, or I can go all the way around and come this way. So I need to indicate that. I can go through a 4K, or I can go through a 5K. And no matter what, once I go through them, I'm where I want to be. And so like I said, I'm pretty sure this is the most complicated of the resistance ones. So now we need to shrink these. I've got a 2K in parallel with a 3K, and a 4K in parallel with a 5K. So we've got 2e to the 3, 1 over x, plus 3. Oh, I messed it up. 2e to the 3, 1 over x, plus 3e to the 3, 1 over x, equals 1 over x. So we get 1.2k for the first one. And for the second one, we get 4e to the 3, 1 over x, plus 5e to the 3, 1 over x, equals 1 over x. And we get I'm going to round that. I'm just going to call it 2.2k. And so if I collapse it one more time, we get 3.4k. And that's it. So this circuit here, I'll scroll up. This circuit here is the same as 0.65 volts with a 3. I was getting better at that. Now I forgot again. 3.4k. And so notice, this was a problem we weren't able to solve because we had no way to break this down. But by doing Thevenin, I can. So remember the question says, what would the current be through a 1K resistor? Well, now that I know what the circuit looks like up to here, I can just add my 1K and solve for the current. So we have 0.65 volts divided by, now remember, we've got 3.4k plus the 1k, so that's 4.4e to the 3. And we get 1.477 e to the negative 4. So remember, we need to put this in proper notation. So if I move this to the right, that gives me 14.77 e to the negative 5. If I move it one more time, 147.7 e to the negative 6. And so 147.7 microamps. And that's it. That was a problem we couldn't possibly solve before, and now we can. Alright, I was going to stop here. I want to do one more example. Just stick with me for one more tiny example. Because we didn't do any with a current source, and I want to make sure I show you that. So I made it real simple. Let's do the same thing for a current source. And notice, using this, we can turn a current source into a voltage source. So if we open it at the load. So I've got 1 amp, 20 ohms, 60 ohms, and I open it here. And so all I need to do is figure out the voltage from there to there. So this one's even easier. We don't have to break it down because we already know the resistance and the current. So notice, if I have 1 amp from here going through this one, then I have 1 times 20, because remember our voltage drop gives us I times R. So we have 1 times 20, which means the voltage drop from here to here is 20 volts. That current, all of it has to go this way because this is open. And so the voltage drop from here to here is 1 times 60, or 60 volts. So if it's ground here, that means the voltage here is 0. And if it goes up by 60 volts to get to here, that means the voltage here is 60 volts. And so the difference from our V Thevenin is 60 minus 0 volts, which is just 60 volts. Now if we want to get the R Thevenin, so if I want to get the R Thevenin, remember we have to remove all the power supplies and we have to calculate the resistance. So remember, with a current supply, that means we open. And so I have this, I have this, and we need to solve for the resistance from here to here. Now look, this is even easier. When I redraw this, the current starts here, and then we have a choice. The thing is, if it goes this way, it's an open circuit, so it can't actually go that way. So like if I were to redraw this, this is open. So that 20 is like it's not even there. If it goes the other way, it goes through a 60, and it gets to where we want to go. And so notice the resistance between here and here is just 60 ohms, because that's the only way it can go. And so if we write our final circuit, we have 60 volts and 60 ohms. That's it. This is our Thevenin. And so we could replace all of this with this circuit right here, and it will work exactly the same. And that's it. There's only 2 more lectures left. 2 more! You can hold on for 2 more lectures! I know it's that part of the semester where we're getting really close to the end. Everybody's excited. They want to leave. Just 2 more lectures, and you've got all of DC under your belt. Talk to you again soon.